5. 3, 2, 1. Go. No. Go. We're live. This is Retraice segment number 73 for Wednesday, December 7th, 2022. 11 p.m. Eastern, 8 p.m. Pacific. Man, I almost had the opening perfect. Retraice is about what's going on out there. The short answer to that question is computer controlled. Long answer, you're not getting it because it's December 7th. It's December to remember, the Math and Code event. If you don't know what we're doing, it all goes back to Artificial Intelligence, a Modern Approach, 4th edition, Russell and Norvig. We're doing there's a lot of stuff to tell you. We'll go back to Re73. I think that's the turning point. You don't have to go back all the way to the beginning, although maybe you want to. I would. I love the old episodes. I don't know why. Re73 is sort of the turning point. It tells you why we're studying AI. I'm not going to go into it today. Today we're doing math. Could you predict it? I thought you could. That's why. Because we have a landscape and we have an equation that comes up on page 120 of AIMA4e. And we're attacking the math, we're attacking the code, we're attacking the things this December that are going to give us, that would otherwise give us trouble in January through June of 2023 as we deep dive and really internalize AIMA4e. But the hard stuff first, front loading the difficult stuff so that we don't get bogged down. There's no tar pits, right? Okay, let's talk about what we're talking about. So far we've covered a lot of stuff around what this equation means. I know that's not helpful. There's Retraice segment number 70, Re71, Re72, Re73, Re74. Oh, no, not that one. No, today's Re73. What am I talking about? And then Re75, if you want to go back and find out more about what's going on out there and what's going on in here at Retraice. This is Retraice segment number 73, the segment you're watching. And these are going to be the notes. This is the basis of the notes. These are the live notes. Okay, so first of all, I just want to call out here our little disclaimer. So I've been putting in the notes pretty consistently almost. I am not mathematically trained, or I am an autodidactic amateur mathematician, which is to say, not even a mathematician. I mean, I just love math, but I don't love it more than anything in the world. I just love it. I should not be your mathematician. You should not take everything I say to the bank. That said, I try really hard to get the right answer, and even if I get or say the wrong thing sometimes, I always figure it out. I never go long periods of time saying the wrong thing, but I sometimes go short periods of time doing that. That's just a disclaimer you should put on all this. I'm your podcaster. I'm not your mathematician. I'm not your math teacher, but we have to talk math if we're going to talk AIMA4e. So that's what we're doing. All right, what is this again? This is our gradient of our function. It's sort of like a slope in a six-dimensional space. It's going to help us. Oh, so what are we working on here? Working on the Romanian airport problem. You've got a bunch of Romanian cities, and your job is to place 3 airports so that you've minimized the unhappiness of all the people in all the cities. And the way we do that is we turn it into a math problem that doesn't culminate in this, but this is the key equation, let's say. So this represents the gradient. I changed the notation a little bit here to put the vector, our guess vector x here. I get this notation from Dyson-Roth et al. Mathematics for Machine Learning. We didn't have that in AIMA4e, but I put it there because it's calling out that we're expressing this gradient here as an operator on this function of this particular solution, the 6-dimensional solution, which is this vector, but put into these denominators. And okay, so I kind of sort of started to figure this out just in the last hour or two as I was kind of finishing up, getting ready with the notes. We're going to get these. So the gradient is like a combination of slopes, like six different slopes. You use partial derivatives to find the slope of each variable that you hold all the other ones still. Yesterday I said it wrong. I said you hold one still. No, you hold the other ones still, and you just vary one of the variables to find out what its instantaneous rate is. Okay, that's partial differentiation. And then you do that for all 6 of them, and then you know that combination, that 6-dimensional slope, is the slope of at the point in your solution space represented by this vector, this little red X, or these 6 independent variables. Okay, and the thing is, like, this is all fancy symbols, and we're going to need to turn this into numbers, and it's not really obvious by looking at it, like, how this is going to lead us to know whatever it's trying to tell us. It's trying to tell us which direction we should go, given a guess point. A guess point is in quotes. It's a guess vector. It's a set of points. A guess vector set of points for the airports down here. Which way should we go? And we get the slope with respect to one axis, and then the next axis, and then the next axis, and the next axis. And we vary each one of these separately in order to find that slope. And that's what we were talking about yesterday, the limit. If we vary using h that approaches 0, this is basic calculus, we're going to find the instantaneous rate of the function, the 6-dimensional function, with respect to only one of its dimensions, one of its independent variables. Okay, so we get this 6-dimensional slope here. Okay, great. What do we do? How do we turn this into numbers? Well, that's that's the most important thing in my mind right now. Like, we have to get this down to an example. We can start with a really easy one, 2 cities, 1 airport. But the thing to remember here is that in order to turn these are scalars. I mean, these are algebraic expressions for what will eventually end up being scalars. In order to turn these into numbers again, right now they're in algebraic symbols, we're going to have to calculate f. It's not the only thing we're going to have to calculate. We're going to have to calculate f, the partial derivative of f with respect to x1, so that's a little bit of a calculus problem. But ultimately, we are going to use the function f, and we haven't actually put the function f into any of our, this is yesterday's notes, written up, part 3, Re73. We haven't actually written anything other than this, which is sort of a misleading representation of f. Why do I say that? In order to calculate f, we have to know the locations, the coordinate locations of the cities. Okay, just for a second here. These 6 independent variables, which represent 3 sets of 2 coordinates each that correspond to the airports, are the things we can move on the map. But we don't move them in a vacuum. The things that give us something to care about are the cities. So we move the airports however we want amongst the cities that are fixed. In order to calculate the value of our function, which is to say how well did we do, or how high is our cost, we want to minimize in this case. You can minimize or maximize. It's basically the same math with one with a negative sign. We want to calculate the cost here of the location, these 3 locations for the airports as represented by this vector. We have to know where those cities are, and we have to do a little bit of trigonometry or Cartesian geometry, and that is not at all represented here. Okay, this is I've said in the past, one of the things that make mathematics difficult are, on the one hand, abbreviation, and we've got, Candy Crush symbols all over our screen right now, and we're seeing all kinds of things we don't know what they mean. But we talk about them, and they start to, if you look at your English alphabet, if you speak English, whatever alphabet, or pictographic and what's the ideographic? Chinese is pictographic and ideographic. Whatever your characters are, they were once Candy Crush. If you were lucky, they were Candy Crush, okay? And really most of the time, it's not Candy Crush. It's just black and white. Look at this. Look at this. Black and white. Boring. I'm going to play some Legos. That's what kids say when they see that stuff. I don't think so. It's only when we talk and yap, and what do these scribbles mean again? Why are the grown-ups getting all upset about the scribbles? Wait. You're telling me if I read the scribbles, I'm going to know what they're talking about? Okay, what's reading again? Show me that. That's how kids eventually become literate. It wasn't always so. It's the same with numeracy. It's the same with, I don't know what the equivalent term for computer literacy is, too clunky. And we need coderacy. Coderacy? Code literacy? All right, so that's what we're going through here when we look at our various equations. And a difficulty that was sort of happening that I didn't really notice until today was that we weren't unpacking this f. Okay? This f involves knowing the values of the city, knowing the coordinates of the cities, and using basically the Pythagorean theorem the Pythagorean theorem to find the straight line distances between the cities and each of their closest airports. So let's say there are 3 cities that are close to this airport, there are 2 cities that are close to this airport, and there are 5 cities that are close to this airport. Okay, we have to take the coordinates of each of those cities and do a little bit of Cartesian geometry to find the straight line distance, because we can always do right angle distances very easily. But what we're trying to square is the straight line hypotenuse distance between an airport and a city. And then you've got to do it for each city. And then you sum those squares. We talked about why we sum the squares. I think we started Re70, I mentioned that, but it's in Re70 notes and Re71 notes. We sum the squares of those hypotenuses, hypotenae, because that gives us a score that changes in a non-zero sum way. If we move the airport 5 units this way, let's say 5 miles toward this city over here, and we're only just measuring the straight line distances, then our score is the same. That's not fair to these poor bastards, okay? But if we measure the square of the distance, the square of 15 squared plus 5 squared is 250, then we can see, oh, the score is high. We want it to be low. We want it to be as low as possible. This is our gradient descent. This is the bottom of our little valley, okay? This is where we want to get to, except we're going to have 3 of these airports and a bunch of spoke-like straight line distances to all the Romanian cities around them, okay? To help us get to that gradient descent is the gradient of f at a point x, a 6-dimensional point x. And the way you calculate it is you find the partial derivative of f with respect to x1, partial derivative of f with respect to y1, et cetera, et cetera, et cetera. But in order to calculate those, in order to turn those into numbers instead of fancy words and fancy symbols, we just want them to be example numbers or worked out an actual problem, stepping through an actual problem. We're going to have to calculate that trigonometry, do that trigonometry on the distances between, or the coordinates, using the coordinates of the airport in this case, and then in the cities around it, and then the airport in this case, and the cities nearest to it, and the airport in this case, the cities nearest to it. That's what you should see when you look at this big thing, okay? And this definitely needs to be here. It's not in the book, but it needs to be there to remind us that this is the gradient of f with respect to, or the gradient, I don't know how this is supposed to, del of x of f, or del of f with respect to x. You wouldn't say with respect to. Del x of f maybe. But the point is, we're taking the function at a particular point and figuring out the gradient or the slopiness, or the shape and slope at that particular point, so that we know which way to go to improve our score. In the case of our particular problem, we want to go downhill and get to the bottom of this gradient. We want to descend all the way to the lowest possible score. Okay. With me so far? Take a breath. We're not going to do that much more, but that needed to be said more clearly, I think, than I've done it. Okay? Now, back to unpacking these partial derivatives. What I've done here is we've got to do 6 of them, okay? 6 partial derivatives. Here they are. There's all 6 of them, okay? You've got the first one, partial of f with respect to x1, and then here's the arithmetic, or the algebra. The next one is partial of f with respect to y1. Okay, so far we've covered, with just these 2, we've covered the 2-dimensional elements, the gradient of the first airport with respect to the, it's saying it in a cutoff way like that. It's hard when you've got the symbols right here. But anyway, this corresponds to the first airport, this is the second one, and these last 2 are the third airport. You can see I've highlighted, oh man, getting that highlight, I just gotta tell you, no, I don't. Never mind. Just pretend that highlight was easy. Pretend I made it look easy. I just did by not bothering you with all the nonsense. Back to the Candy Crush. So, this is the only difference in all of these sides of the equations. We only change the independent variable with respect to which we're taking the partial derivative of f. And over here, the way we do this varying, you can't capture this easily in the equations. But what we're doing is we're adding h and h can be a positive or negative number, it doesn't matter. And then subtracting, finding the gap or the difference between the original value of the function and the value of the function with h added to x1, the x1 variable. All these other variables we're holding the same, okay? These all stay the same. We only want to find the slope on one particular dimension. So we hold all the other ones the same, and we calculate a limit. And a limit's kind of it's a thing you get used to. And you know, I just read this thing. Where was it? I think it was in Dijsselhof et al. Please just be where I remember you being. Please, what other thing would I have been reading? I don't even know. Oh, it's in my new linear algebra book. Darn it. Oh, I don't have it. Everything's going wrong. Anyway, von Neumann said once, according to this frontispiece where I saw this quote for the first time, I'd never heard that he said this. Von Neumann was a great mathematician of the first half of the 20th century. Nobody understands mathematics. You just get used to it. If von Neumann said that, this guy was brilliant. Everybody says he was like Newton level brilliant mathematically, and not just mathematically. I mean, the guy's, I think his parents were in finance, or what his dad was, and he was worldly savvy in addition to being great at math. And he did a lot of important work with World War II and blah blah blah. Nobody understands mathematics. You just get used to it. If he said that, then you need to relax. You need to stop thinking you're supposed to understand this stuff. You're not supposed to understand it. You're supposed to get used to it. When you see this and lim h arrow 0, what you say, the limit as h approaches 0 of the function f of these variables minus that over h. Okay? Or we can say, putting it in the broader context, since we're doing this, we're deliberately holding these variables still while we mess around, slide this one around to find that instantaneous slope. The partial derivative of f with respect to x1 is equal to the limit as h approaches 0 of f of x1 plus h, comma, y1, blah, 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 minus f of the matrix x, or the vector x, over h. It's just how you do it. You can trust me. If you go try and verify these equations, I do this. Like, I do this all the time, and not all the time now, but when I used to study math, I did it all the time. Like, I never trusted anybody, even like Napier and I mean, just nobody. I trusted nobody because it never made sense to me unless I went and, actually did it myself. It makes it sound like I did more than I did. I didn't do that much, but like functions and exponents and logarithms, I didn't trust these. I figured maybe I'd discover some error. No, I didn't think that, but I still had to do it. If you go and do that, you're gonna agree with this. The way this is gonna stop looking like Candy Crush and start feeling like a tool that you can use to find an instantaneous slope in a six-dimensional space that is part of what this six-dimensional slope that you want to arrive at when you've got your actual numbers to plug in. You're just gonna do a few problems. Just do a few problems, maybe do a couple of two-dimensional problems. That's what we're going to do here. We're going to maybe start with a two-dimensional and go up from there. We do it but ultimately to solve this problem, we're going to have to use f, which is not anywhere printed in my notes, but I'm going to work that out. I got to figure out an economical way of doing that. And so, yeah. So these are the 6 partial derivatives expanded out. I've highlighted the parts that change. So you can see here, you're varying the axis y3 and holding all these still, okay? And then, there will be maybe some more annotations in the notes when we're done with that. Okay, that's it for today. I don't think we have any amendments or anything. Check out the website. I'm not going to show you every time, even though I want to. I like the website. The website's cool. It's useful. And I use it all the time to get to links and especially to get to the notes, and you can search the notes and all this cool stuff. All our notes are in the all the references are in the notes. PDF notes are preferable. That's like where it's beautiful and easy to read, but it's all searchable in plain text form as well at notes.retraice.com. If you want to check out AIMA4e in 5 minutes, we did a video on that. Which one is that? Which one? Oh, come on. Just go look at the website. We're having fun here. We're having fun, although it's not a perfect website, and sometimes the thing hasn't been loading, but it's not our website. We didn't build it. We're using a third-party provider. Yeah, Retraice 62, Re73, AIMA4e in 5 minutes. You want to listen to it? Let's listen to it. Oh, this isn't as fast as a YouTube video. Who would have thought? Well, anyway, it's getting there. Oh, for Pete's sake, you're making me embarrassed. 4, there we go. 3. Oh, he's counting 2. Down. Something's going to happen. 1. Oh, this is Retraice segment number 62 for Saturday, November 20. Bays nets. Oh, Bays nets. Of course, Bays nets. Why not Bays nets? You can go there and get the whole book, AIMA4e, in 5 minutes. And I'll let you be the judge. I think it's pretty good. Okay. Retraice.com, Retraice.com. I'm not going to talk anymore. All right. This is segment number 73. Same time tomorrow, 11 p.m., 8 p.m. Pacific. Signing off.